Okay.
It's not a deal with virtual finance.
Okay, everyone, can I have your attention? I want to introduce our speaker today. This is Oomman Varghese. He is an associate professor at University of Houston, and today he's going to be talking about nanomaterials. So, I want to give a little bit of his background in case you guys haven't seen it on the web. He has his PhD in physics from Indian Institute of Technology, which is one of the absolute top science engineering schools in the whole world. He's currently an associate professor of physics at University of Houston. He's been there for how long? Like
6 years.
6 years.
Yeah.
Yeah. And his group is primarily focused on developing nanoscale materials and heterostructures and investigating kind of the unique properties of these materials. And when I say nanomaterials, I mean things beyond, like you may have heard about carbon nanotubes. But what they've done is they've actually made nanotubes out of many different materials, which I'm sure we'll talk a little bit about. I think this is your second talk here.
Yes.
Yeah, it's the second time he gave a talk here a couple years ago at Clear Lake, and that was back when we were in the old building. So with that, I guess I'll turn over to our speaker.
Thank you, Professor David. Good evening. So I would like to talk a little bit about what we are doing in our lab, and in connection with the topic of our today's presentation, which is materials at a nanoscale. So before what I'm planning to do is to give an overview of why we are doing this study and what are nanomaterials, what are the unique properties we have observed in our research. So I hope all of you are in physics, have a physics background, or how many of you have an engineering background? All physics? Okay, good. So the materials physics is an interdisciplinary area. So that has not only physics but engineering, and it involves other subjects also, like chemistry, biology, and all. So we will have almost a cocktail of everything when we go through this the presentation. So stop me anytime if you have a question, and we will discuss there. And if you are sleepy also, raise your hand. Then we can have some exercise. So we have a remote, David? Remote or just?
Oh, yeah, just have to press the keyboard.
Yeah, okay. So my lab is Nanomaterials and Devices Laboratory. There we develop the nanomaterials and develop the devices and the processes based on these nanomaterials. So let me start with the what is a nanostructured material. I know most of you are familiar with all this nano, the term nano. But in the field of, it comes under the field of the broad field of condensed matter physics. Materials, solid state physics is a part of the condensed matter physics, and the nanostructured materials comes under this topic of solid state physics. So what is a nanomaterial? The materials with dimensions, at least one dimension, less in the range of nanometers or in the nanometer scale. Usually we say if the feature size is less than 100 nanometer, it is a nanometer scale, nanomaterial. So depending upon how the material is confined in space, we call it as 0, 1, or 2-dimensional. For example, if you take a very thin sheet, ultra thin sheet, where the thickness of the layer is in nanometer or in angstrom, we call it, and the other two dimensions can be anything. It can be millimeter, meters, or kilometers. But still, as long as the thickness is less than few tens of nanometers, we call it as a nanomaterial. And this particular structure is called a two-dimensional material. One-dimensional material, we can. So this is an example of a two-dimensional material. We will discuss this material in particular later. But you can see that this is a sheet, very thin sheet, but it is extended in micrometers. The other structure is a one-dimensional. One-dimensional means the length can be in microns or millimeters or anything, but the diameter, for example, a wire, if you take the diameter, should be in nanometer. So an example is a nanowire. This is a silicon nanowire. And the other is a nanotube. Nanotube is sometimes called a quasi one-dimensional material because it has the circular shape, because of the circular shape, which is different from the hollow circular shape, which is different from the nanowire. But generally, these are one-dimensional materials, nanomaterials. And then finally, the zero-dimensional nanomaterial, which is the nano particle or a quantum dot or a nanocrystal. All these are used for the nano particle. Generally, the quantum, the dot has the dimensions less than 8 nanometers, 10 nanometers typically. But nanoparticle means the diameter can be 100 nanometers. So there, it is a zero dimension because it is confined in all three dimensions. All three, the spatially confined in almost all three directions. So that is why it is called a nano particle or zero-dimensional material. So these have only a few. For example, if you take a nano particle or a quantum dot, it has only a few hundred atoms or 1,000 atoms. That means we are utilizing some of the unique properties of the atoms. That is the benefit of these nanostructures. We can explore, we can find some of the unique properties and exploit it for different applications which we are interested in. So these are the three different types of nanomaterials. So in our lab, we utilize these properties for primarily three applications. One is the solar fuel generation. So there are two types of fuel generation process we are interested in. One is the hydrogen generation via water splitting. The other one is the carbon dioxide recycling or carbon dioxide to fuel conversion. Then the second project is the hybrid solar cells. That is the latest type of solar cells. And the last, the application is the sensors for medical diagnosis. So we will discuss this briefly. I don't want to go into too much details, so I don't want you to be bored with all these research-specific things. Now, what is the benefit of low-dimensional architectures? So if you take this as a nanotube, the center one is a nanotube. So there, this particular material provides tremendous surface area. What do we mean by that? Surface area. If you take a 1 centimeter, a film of nanotube, say array of nanotubes confined in a 1 centimeter square, and if you unfold these tubes into sheets, if you cut this into and make sheets out of these tubes, the area we get is much more than 1 centimeter. For example, if you take a nanotube of length around 20 micrometers, diameter around 100 nanometer, and we unfold it, we will get 1,000 times the area it occupies, flat area it occupies. That means a lot of surface for either to absorb light or do the chemical reactions, or whatever we want to do, we can use with we can do with that surface area if it is surface area related. The other property is some of these materials can transport the charges very easily through this material. So for example, if you take a light absorbing semiconductor nanotube, so light generates the charges, electrons and holes. The electrons, some of the materials pass electrons easily through the material, whereas the holes can be supplied to the surrounding for oxidation reaction. So this is what is used in photocatalysis. Then this is the case of one-dimensional material. So the two-dimensional material, one example is graphene. All of you know graphene is what? Exfoliated graphite. So we take graphene, and there are a lot of properties unique to graphene. We are not going to the graphene stuff today, but we are interested in some other material which are oxides semiconductors in the form of graphene, 2D materials. So these materials also, and all the 2D materials or the particles or the quantum dots or nanoparticles, they can exhibit the charge transfer much faster than the bulk material, or they can show the quantum confinement effect. That means the size effects will be much evident in the case of nanoparticles. A good example is the bandgap variation. If you take a material with that absorbs light up to the red region of the solar spectrum, and if we take that bulk material into very small to quantum dot, and then it bandgaps widens. That means it can no longer absorb the red, but it can absorb blue or green depending upon its size. So we can tune the light absorption of these materials by just tuning the size. That is, this is a well-known fact, well-proven fact. So I am not going into the details of that. So this is one example of a nanoparticle. So this nanoparticle, this picture is from, I don't know how many of you are familiar with solid state physics, by Introduction to Solid State Physics by Charles Kittel. So so probably when you learn solid state physics, that is one of the fundamental books followed by the solid state physicists for undergraduates and graduates. So here you can see nanoparticle, and these are the reconstructions of the reconstructed images of the atoms. You can see, you can count the atoms from the nanoparticle. The size may be around a few nanometers, but we can count. That is why I said the nanoparticles can have hundreds or thousands atoms, less than that. So that is why they exhibit unique property. This is a high resolution transmission electron microscope image of the nanoparticle. And why the nanoparticle or a nano? An example I can tell. So if this particle absorbs light, solar spectrum, then we can use it for water splitting. Sometimes, of course, it has to satisfy a few other criteria. Assume that all criteria are satisfied. Now we have a nanoparticle of such a material, and so we shine light. So what happens is the charges are generated. So if you have the valence band, the electrons in the valence shell will be excited by the light to the conduction band. So the electrons can move and cause the reduction process. And the holes generated, the positive charge can do the oxidation of the water. The problem is that if the size is too large, means if you take a micron size particle, these charges, electrons and holes generated by light, can recombine and lost. That means they cannot do any chemical reaction. That means we excited the material, but that is of no use to us. So, but if you reduce the size to quantum, the dot or a nanoparticle, like similar to this, the charges can immediately get transferred to the surface, because the surface is not far from where they are generated. They can move to the surface, and the electrons can cause the water to reduce the water, and the holes can oxidize the water. So that is how the hydrogen and oxygen are generated. So the nanoparticles, this is one of the unique properties of the nanoparticles or nanomaterial. Now, why we are doing all this nanomaterial? Just for the curiosity of what is going on in nanomaterial, or whether any other reason for investigating these nanoparticles? This is a picture when I went to Los Angeles. This was in the news, and this is a picture showing the pollution in the smog in LA. This is not only a problem in the LA, but this is a problem all over the world now because of the several reasons. One is the particulate emission. The particulate means very, very small particles, microns or nanometer size particles are emitted to the atmosphere due to various processes. So that kills around 3.3 million people per year, just because of the particulate pollution. And the particle PM 2.5 is the size, the particulates of size less than 2.5 micrometers. That means extremely small particles. These are really harmful. So those are the main leading cause of this problem. Second, atmospheric carbon dioxide is increasing. So you know what is the current level of carbon dioxide in the atmosphere? It is much more than 300 now. Now it was a few years back. It was 300, and I think if you take the history of the Earth, most of the time it was around close to 300, 280 pp parts per million. And a few years back it was 300s. Now it is 410. It is increasing very fast. Another problem with the pollution is high ozone level. So high ozone level is LA. That is a big problem. High ozone level. Ozone is created by the interaction with the reaction between oxides of nitrogen and volatile organic compounds emitted by the automobiles, industries, and all those things. So these are real problems world is facing, and it is increasing. We don't have a solution at the moment. This is the particulate, the map all over the world. So if you can see that here the particulate-based pollution is much more in red regions. US is okay compared to this, but not safe still. We also have the problem of the particulates. So this is based on the severity of the pollution. Now, what we do, this is one of the side work we do. This is in collaboration with our Toyo University in Japan. What we did was that we studied what is the effect of the nanomaterial on the human body or living cells. So we studied the toxicity of this material. So this is nothing but this is a nanotube of titanium dioxide. Titanium dioxide is the biocompatible material. If you go to your grocery store and get some food, and you read the ingredients, you can see titanium dioxide in it. That is used as an anti-caking, antifungal agent, a lot of applications. Titanium TiO2 is used in this. And so this is a biocompatible material. But when we did the toxicity studies, we found that the nanotubes can penetrate the cell and go into the cell and destroy the nucleus. That means it has genotoxicity. So it can destroy the nucleus. So that is a biocompatible material in the bulk form. When it became a nanomaterial, it has this problem. But there are opportunities. So that means we cannot just inhale all this nanomaterial. Some are very toxic. We have to be very careful, even if they are benign in the bulk form. So, but we are thinking of using it for cancer treatment without drugs. So you can kill the nucleus as we need, and then we are planning to use that property. Now, coming back to that was the particular problem. Coming back to the carbon dioxide environmental problem. So this is the Arctic ice coverage So you can see this line. This is the average over several tens of years, and this is the this was the coverage in 2008, a few months back. So that means the very drastically the coverage, Arctic coverage, ice coverage is decreasing, and the Antarctic coverage also is not very impressive. There also there is a change in the coverage of the ice coverage in this region. So if you want more details, so if you see the graph, how the extent of ice is reducing, this is the graph from 1980 to 2016, almost linearly it is reducing. So now, why do we? So if you need more about this, you read this article. It's a very nice article about this. But why do we need to worry about these things? Why physicists should worry about this? Yes, yeah, a lot of. It is the main problem. One of the problems is global weather pattern will change. Arctic ice will ice decides the thermohalion circulation, the ocean current, the warm Gulf Stream going through the Europe to make the Europe warm. That is no more there because there is no ice for the hot water to flow to the Arctic region. So these are real problems that the world is facing now. Earlier it was a matter of debate. Now it is a real problem which we have to address. So this the United Nations constitute a panel to immediately report about these problems. And this is if you are interested, you can read this report. It's available online. This is the IPCC Intergovernmental Panel on Climate Change. So they said that by 2050, the increase will be around 1.5 degree Celsius, the average increase. But that is enough to cause a lot of problems, dumping a lot of land under water, and creating a lot of problems in the whole world. So I'm not going to the details of that, but if you see the correlation between the carbon dioxide and the global temperature increase, this is the average, the temperature that has been there for centuries or millennia. So around, so you consider it as zero. That is a baseline, zero level till around 1940. Then it start increasing, and from 1980s, it is almost linearly increasing. The average global average temperature. Now you think that it may be just a moment, a few years, it can come back. That if you see the increase, the carbon dioxide emission, you can see the correlation. See, this is the carbon dioxide emitted till around 1950s. Then when we started using coal, we were using it before, but started using oil extensively, it was increasing. Now you can see that what is the slope of the curve, the carbon dioxide, and this matches very well. If you overlay this, will match very well. So that will clearly say what is the effect of burning the hydrocarbon fuels. So now if you burn the octane or take octane, pure octane, if you burn it, burning means it is what is the oxidation process, right? So when you burn, you will get what? When you burn octane, what will you get? Or when you burn any hydrocarbon, what will you get? Stoichiometry, carbon dioxide and water vapor. So now, how much carbon dioxide will you get? If you take a 1 liter, assume that density is 1, so 1 kilogram of octane, if you burn it, you will release 2.3 kilograms of carbon dioxide. So in my trip from University of Houston to here, at least I might have emitted 7 to 8 kilograms of carbon dioxide, just my trip to UH Clear Lake. So you can imagine how much we are all responsible for, how much CO2 emission we are responsible for. If you take the US carbon dioxide emission so these are in billion metric tons, the carbon dioxide emitted So the petroleum, the deep blue, the natural gas, then the coal. But US has been, since 2010, we have been consistently reducing the emission. But still, you can see that it is a 5 billion metric tons of carbon dioxide. US, this is the case of US alone. So that reduction is due to the increase in the efficiency of the processes, the use of the natural gas, which has less carbon. And these are some of the reasons for this. But still, if you take it all over the world, each person in the world is responsible for around 5 metric tons of carbon dioxide per year. So that is the amount we are dumping into the atmosphere. And again, remember that only 25% of this carbon dioxide is absorbed by plants, and 25% by ocean. Rest 50% will stay in the atmosphere. Where does it go? It doesn't go anywhere because the carbon dioxide is very stable. So that is where the problem comes. Now, what can we do? So this is one of the projects which we are doing, how to address this pollution problem, carbon dioxide problem. We will come back to that later, but let us see what why we are how we are making the nano materials. One example is oxide nanotubes. This is just one of the materials we prepare. This is not carbon nanotube, but we can make the similar to carbon nanotube. We can make nanotubes of a lot of different materials. We are interested in oxide semiconductors. You know why oxide? Oxides are stable. We don't have to worry about oxidation problem. Silicon, if you take, it can oxidize immediately. But these oxides are very stable, and they can show this. They have semiconducting properties also. Some of the oxides. So we are interested in making the nanotubes of those materials. This is the nanotube of titanium dioxide, which I participated in developing several around in the beginning of 2000. This is titanium dioxide. The length of the nanotube was around 0.5 micrometer, but the diameter is diameter we can vary from around 15 to 20 nanometers to 400 nanometers. A large range we can increase the diameter. This is a nanotube sample with this gray. This region is covered with the nanotube, and the top surface is the substrate, which is the titanium foil. So this is our different images of the nanotube structure. You can see from this image you can see the hollow inner region of the nanotube. So now, if we look at the transmission electron microscope, you can see what is there in the walls of the nanotubes. I don't know whether you can see clearly. You can see the crystal lattice. So these nanotubes, when we prepare it, these are amorphous. Amorphous means these are a lot of recombination centers. So electrons and holes can be combined immediately. So we cannot use it for any of the applications like photocatalysis or solar cells. So we want to make it crystalline. So we heat treated the material and crystallized it. Then this is how the crystallites are formed inside the wall of the nanotubes. So this is one crystallite, this dark region, and this is another crystallite. So these crystallites are formed, and if you increase the temperature of heat treatment, this will merge to form a single single network of the crystallites. That is how the whole nanotube wall become crystallized. Remember that the thickness of the nanotube wall is can vary from just 2 nanometers to a few tens of nanometers. So that we can adjust the thickness of the walls. This is another image of the nanotube array. These are grown by the process called anodic oxidation, and where these nanotubes are spontaneously formed. We don't have to put any template. It is grown automatically. The test tube like. So the bottom surface is closed. The top is open. So these are the different types of nanotubes. These are long nanotubes. We can go to even millimeter length by keeping the diameter still in the nanometer regime. And depending upon the application, we grow the nanotubes either on glass or film or this is the nanotube array grown on the wire, titanium wire. So it is titanium wire, and the tubes are grown radially outward. So this is used for an application called phosphoproteomics to separate the phosphorylated protein. So this is for the study of proteomics. So this is so far we just passed through the titanium dioxide nanostructure. This is another nanostructure we developed. This is zinc oxide. You can see the straw-like nanotube grown on the surface of the nanotube. We will discuss the application later. Now, why we are interested in the nanotube structure rather than other structures? One reason is that these nanotubes can be attached to a surface, not like particles. Particles can fly away unless we make a paste and make the film out of that. But these nanotubes can be attached to a substrate. So these cannot, these do not fly away and cause environmental problems. That is one thing. But for applications, these nanotubes provide us the very high surface area, as we discussed earlier. And more than that, the wall thickness of the nanotubes, here you can see the crystallites. The wall thickness of the nanotube is in a few nanometer range. So if it absorbs light, the charge carriers are generated in the wall, and these electrons and holes, the charges, can easily come to the surface before getting recombined. So the large surface area, as well as it facilitates the charges to come to the surface for the reduction or oxidation reaction. Now, so with these nanomaterials, these are developed for different applications. Not like we just sit and develop a lot of nanomaterials and find applications. It's not like that. These are materials developed for the application, particular application. So sometimes we get unexpected results. Nanotube growth was like that. We were aiming at making nanoporous structure of high surface area, but what resulted was a nanotube structure. So that is how research can go completely in unexpected ways. That's the beauty of research. So now we do the fundamental studies of the nanotubes. This is you can see this is a 4-probe setup. I don't know how many of you are familiar with the electrical transport measurements using 4-probe method. So this has 4 probes, and this is a single nanotube of titanium dioxide. And this can be heated on one side. You can see the heater coils, or both sides, whatever we want, and we can study the electrical properties, thermal properties, and the structural properties of the same nanotube using this arrangement. This is called this is a micro device. So these are the nanotubes we studied. What we observed was that the nanotubes in the stoichiometric form, these are the nanotubes in the stoichiometric form. That means 1 titanium and 2 oxygen, TiO2. Now it has reasonably good thermal conductivity. But if you are heat treating this hydrogen, we can remove some of the oxygen from the lattice. That means we are reducing the lattice. If you reduce the lattice, the thermal properties are completely now different. Thermal conductivity is now very low. It has gone down here. The black and the green. So now we studied more into the details of this property, and then we found that electrical conductivity is higher for this material because the hydrogen reduces the oxygen, and these oxygen vacancies are donors, electron donors. So they have the high thermal electrical conductivity. But at the same time, when we studied the Seebeck coefficient, we found that the changes from negative to the positive value. Negative Seebeck coefficient means material is n-type, as expected. Titanium dioxide is an n-type semiconductor. But after reducing, it behaves as an n-type semiconductor at room temperature. But when you reduce the temperature, so you can see that when you reduce the temperature to around 175 Kelvin, the Seebeck coefficient becomes positive. That means the material has become p-type. That means holes are rich in that material. So that was never been observed. So this is the first time anybody is observing the transition at low temperature in single nanotube. But the bulk materials, nobody observed this. So, but the temperature, when we increase the temperature above 175, material transfers back to the n-type. So these materials have n-type and p-type transition. These are much importance in many materials. For example, for many applications, thermoelectrics. This can be used in low temperature thermoelectric application. So just mentioned the application. So this is the the Seebeck coefficient, positive Seebeck coefficient, and around 175 it becomes positive. So that transition from n-type to p-type was occurring at that temperature. Now, what we think was that the oxygen vacancies, they create those are defect states in the gap of the band gap of the titanium dioxide. Those are dormant till the temperature is low. When the temperature is low, they accept the electrons and make the material p-type. That means hole-rich material instead of the electron-rich material. So this is just an example of the unique properties exhibited by the nano materials. So I want to go to the different fundamental properties. Let us go to the applications. 3 applications I'm going to discuss briefly. One is solar cell. So the first one is solar cell. So we used this material to the titanium dioxide nanotube first to make the solar cell. But for solar cells, we know light has to go and incident on this material so that it can absorb. So there are 2 problems. One, we were using it. You saw the picture of the nanotube sample. The substrate was a foil. It is opaque, and the film was coated on that. So that material, that substrate could not admit light into the titanium dioxide. So we had to replace that substrate with a glass. That was a big challenge, but we overcome that. So we deposited the titanium film, thick film, on the glass. And then we did the anodic oxidation process. And then we heat treated. So this is the metal film, and here is the nanotubes grown on the top of the glass. So these are the images of the nanotube. Because of the porous nature of these films had a very low refractive index. So it had anti-reflection properties. You can see this. The transmittance increased when a film of nanotube was coated on the top of the glass. So the transmittance increased from 82% to 90% around because of the nanotube. Now the other problem was that this material, to be used in a solar cell, titanium is transparent. It absorbs only ultraviolet. It has a band gap of around 3 to 3.2 electron volt. So it cannot absorb solar radiation. So we have to use something else. So we developed the dye-sensitized solar cells based on that, this material. So we stained the high surface area nanotube, titanium dioxide nanotube, with the dye, appropriate commercial dye. We can use even natural dye also, but some are not very efficient, so we use the commercial dye. But we found that the quantum efficiency was very high for that dye. So this shows the quantum efficiency. Quantum efficiency means it tells you how many electrons or hole pairs are generated and driven to the external circuit per incident photon. That means 1 electron, or if you are shining the material with 100 photons, how many photons are converted into charges that are flowing through the external circuit? That's the quantum efficiency. So quantum efficiency of 50% means there's a 50% of the incident photons are converted into charges flowing through the circuit. So we found that there's a large quantum efficiency up to around 80%. That means 80% means 80% of the photons are converted into charges. There's a very high efficiency for this material. So that is one of the earlier work we did that demonstrated that this material has potential. In nanotubes in the array form, they can give quantum efficiency in a very large range. Usually in a dye-sensitized solar cell field, people use large particles to scatter light and increase the quantum efficiency. But in the case of nanotubes, we didn't have to do that because the materials, these nanotubes scatter light, and that scattered light is reabsorbed by the dye. That way the quantum efficiency is really high. So this was the earlier work we did, and now the very recent work is on perovskite solar cell. Perovskite material has a structure of AbO3. That's the structure. The barium titanate, strontium titanate, all these are examples. These are conventional inorganic materials. But recently, there's some organometallic compounds of this structure have been developed. Methyl ammonium lead iodide is one example. So methyl, it has a perovskite structure like a barium titanate or a strontium titanate. So this material is, people found that this material is really good. But the problem was that this material is organic material, it's very unstable. If it sees water vapor or humidity, if you expose it to humidity, it's gone. Immediately it changes the properties, no more a good material for solar cell. Or oxygen, interact with oxygen, it can be a poor material. So the stability has been a problem with the solar cells. We can have efficient solar cell, but if it is not stable, what is the use? We cannot manufacture the modules out of it. So, but when we used the nanotubes, what we did was that we fill, these are nanotubes filled with this material, impregnated with methyl ammonium lead iodide perovskite. That absorbs light. Titanium dioxide doesn't absorb light. But what it does is that it transfers charges from the perovskite to the external circuit. That's what the titanium dioxide does, nanotube does. So what we found that we got an efficiency of 15%. That means 50% of the sunlight is converted into electrical energy. And more importantly, we observed very high stability in these nanotubes. Normally, these should be encapsulated, but we tried without encapsulation and found that these solar cells made of titanium dioxide are much more stable than those made by other material. So what the reason is that you can see the nanotubes. The nanotubes spacing we can adjust. These are nanotubes on glass with widely spaced. Now when we fill this with the perovskite light absorbing material, this acts as a template. Oh, sorry, the scaffold for protecting the organometallic materials, which is unstable. So this oxide encapsulates the perovskite, the methyl ammonium lead iodide, and gives stability to that material. So earlier we were talking about the surface area, high surface area for charge transfer.
Sorry, I need to check something up here. The caption has just lost the sharing on the slides.
Oh.
Okay. All right. For some reason, this has happened before. Okay. Thank you.
So this is one of the this is one application which we are studying, how this material can be used for solar cell application. The other one is the solar fuel generation. We can generate the fuel like water. We can split water and generate hydrogen and oxygen if you give energy to that. The sunlight is the sustainable way of producing or generating energy for our needs. So we use a process called photocatalysis or photoelectrochemical conversion of the water. So what we do is that we disperse either the nanoparticles or nanotubes or two-dimensional nanostructures inside water and shine light. And we can, the electrons and holes are generated, as I explained before. These are not far away from the surface. They can cause the reduction and oxidation to produce the hydrogen and water. But the problem is that this is not sustainable. Most time, after some time, these particles can lose its surface properties, and it can reduce the activity. So what we do is that we use a photoelectrochemical ways to generate hydrogen. That means we have a nanostructure, we shine light, but we apply a small electrical voltage so that the charges generated from the material can, electrons generated can flow to the other electrode. For example, this is the anode, this is the cathode. So here the light absorption creates electrons and holes, but the electrons are immediately driven through the external circuit to the cathode. So where the water reduction takes place and hydrogen is generated. And here in the anode, oxygen generation takes place. The overall reaction is this: water plus light is hydrogen plus oxygen. Now we need at least a 1.23 electron volt energy for this to happen, the water splitting to happen. Other process is carbon dioxide to fuel conversion. So it's the same way. The charges are generated instead of reducing and oxidizing water. Here the carbon dioxide is converted into fuel. So if you mix the carbon dioxide and water vapor, we'll get methane out of that. And the methane can be used for, we can burn it, or we can use it for in a fuel cell to generate the power. But the byproducts are again carbon dioxide and water vapor. So this can be again sent to the recycler to convert back to the methane. So that means it's a carbon dioxide recycling process. So environmental damage can be reduced by using such processes, because we are not releasing the carbon dioxide as free gas into the atmosphere. I'm not going to the details of this, but let me tell you what we have the solar spectrum ranging around 280 nanometers to around 2500 nanometers. Out of that, because of the restriction that we can use only 1.23 electron volt per photon, we can use up to around 1000 nanometers. So in the near infrared region, right? But because of the other practical reasons, the harvestable wavelengths ranges up to around 800 nanometers. So we need a material with a band gap around 2 to 2.2 electron volt to convert to absorb light and do the fuel generation process. So this is the conventional semiconductor diagram, where we shine light and we can excite the charges to the conduction band, and these electrons can be used for the reduction. Or the electrons, if the high energy photon is incident, this can go really to the high in the conduction band, where the energy can be lost due to thermalization, and it can come back from to the bottom of the conduction band and make it transfer. So this here we are losing some energy, high photon energy. So we were trying to utilize this energy also, so that we can improve the efficiency of the process. So the ideal efficiency of the process is around 31%. That means we can convert, using a single material, we can convert sunlight to fuels around 31%. That is the ideal. But if you practically, the efficiency goes down to around 17 or 18%. That is the expected efficiency when we develop a process for carbon dioxide conversion or water splitting. So when we use titanium dioxide for the water splitting, in photoelectrochemical water splitting, we found that the quantum efficiency is very high in the ultraviolet region. But if you go to visible region of the solar spectrum, above 400 nanometer, there is no quantum efficiency. That means there is no fuel generation. There is no chemical species generated using the visible light. That means the process is very inefficient. Only ultraviolet light is only around 4 or 5% of the total solar this photon flux. Now what we did was we do different strategies. Just I want to explain one strategy, that is the doping. We put impurities inside the crystal lattice of titanium dioxide and make it absorb visible light. That is one strategy. So here is a titanium dioxide nanotube doped with nitrogen. So nitrogen doping shifts the band gap to around 2.4 electron volt. That means from UV range to around green region of the spectrum, solar spectrum. So this we utilize for converting the carbon dioxide and water vapor to methane. So this is the chamber we used. We shine light, we fill with the chamber with the carbon dioxide and water vapor, keep a titanium dioxide film there, and then the carbon dioxide reacts with the water vapor and generate methane, or even other alkanes are generated. Very recently we changed the strategy from doping. Doping had its own problems, so we changed the strategy. Now our what we work on coating the titanium dioxide with very thin 2D materials, two-dimensional materials, so they can absorb light and transfer the charge to the titanium dioxide nanotube. So that way we can use very inexpensive light absorbing material. For example, rust, Fe2O3, iron oxide can be used as a 2D. If we can make a 2D material of iron oxide, we can coat the titanium dioxide nanotube with that very cheap rust and generate fuel out of that. That was the idea. So with the collaboration with the Rice University and Cochin University in India, we developed a process for that. So we exfoliated hematite into new 2D material called hematine. We call it as hematine because it's like a graphene. It's coming from hematite. So this is a two-dimensional material of iron oxide. So the material, you can see the very high resolution image of the hexagonal lattice of the iron oxide. These are the atomic the reconstruction of the lattice atomic arrangement of Fe2O3. So the material, this is the ore. You can see the settled ore, and then if ore of the iron is hematite, we subject the ore to ultrasonication, and then these 2D structures are evolved out of these ores. These are exfoliated out of the ores. So you can see the color becomes brick-like. That is the color of the iron oxide. Then we coated the titanium dioxide nanotube with this material, and we found that, so originally the nanotube had only the quantum efficiency up to around 400 nanometer. After coating the hematine, we could extend the quantum efficiency to 500 nanometer. So that means we are now broadening the light absorption so that we can increase the efficiency of the process. So up to around 12% only we got with this material. But still it shows that we can broaden the light absorption using this approach. But what was remarkable was that the band alignment of the conduction band and valence band of the iron oxide and titanium dioxide, those are mismatched. There's no way electron can transfer from iron oxide to the titanium dioxide. But we observed through quantum efficiency measurement that indeed it was happening. So the only way it can happen is that the high energy photons can excite the electrons to the upper energy levels of the conduction band, where it can transfer to the titanium dioxide conduction band. There is something called similar to the hot electron transfer. The energetic electrons are transferred to the conduction band of the titanium dioxide. That is how we got the quantum efficiency in the visible light region. Another material we tried very recently is the quantum dot. This is a particle of a few nanometers. It's called boron nitride. So we fluorinated boron nitride and made boron nitride is a wide band gap material. When we fluorinated, it created the gap states, and that made it absorb light. So now in the fluorinated quantum dots can absorb light, visible light. So that's what we sensitized the nanotubes with these quantum dots. And again, we studied the quantum efficiency. This time, the quantum efficiency was much higher. So earlier it was 12%. With this material, we could go to around more than 550 nanometer, around green yellow region, and the quantum efficiency went up to around 25%. So this is a strategy we are investigating now with the new materials. Whether can we get a quantum efficiency of 80% throughout the visible light region? In that case, we'll get a very high efficient photocatalyst. That's what we are investigating right now. So this is the hydrogen generation data, which shows a dramatic increase in the hydrogen generation rate with respect to the titanium dioxide nanotube coated with the boron nitride. The last application is the medical diagnosis. We develop the sensors using the semiconductor materials for medical applications. Here, this is a letter to the editor from a journal, the Lancet, which is a very high-profile medical journal. So it came in 1989 that a woman, 44-year-old woman, came to their clinic, and she complained that there was a lesion on her left thigh. So she said she noticed that because her dog constantly sniffed at it. Even though she was covering, it was coming again and exact that the location. So she was suspicious about that, and she went to their clinic to check it. And they took the sample biopsy, and they did the biopsy and found that it was cancer. So that they communicated that to the journal. This shows that dogs has the ability to sniff the cancer out. So now, later on, there are many people. Many people reported similar things, and now the dogs are being trained for cancer detection, especially the breast cancer, skin cancer, and all those things. So in Europe and even in the United States, now the dogs are being trained for this. But it's an expensive process. So, but can we do that artificially in a very cheap way? That's what we were trying to investigate. So what the idea is to take the breath samples and see whether it can be connected to the disease state of the body. The dogs can smell something. That's why they are attracted to the tumor. So that means there must be some odor or a gas coming out of our body that is a signature that is a signature of the disease state of the body. So this the exhaled gas analysis has been used since I think the ancient Greece, and the people used to test the odor and diagnose the diseases, the physicians. So this is one of the apparatus used in 1898 for the breath analysis. A very crude system. Well, Linus Pauling was a big supporter of this exhaled gas analysis for disease diagnosis. So this is a gas chromatogram of one of the from one of his papers, Linus Pauling's papers. So now there are sensors that detect oxides of nitrogen, especially for asthma, diabetes, all these things. But our intention was to see whether we can detect cancer in the early stage. So we did we developed the nanotube, the zinc oxide nanotube for that applications. You can see this is anodic oxidation process. Initially, these wires are formed, but after some time, these wires are drilled. You can see the small indents on the top, and these are the hole is drilled through the nanotube, not manually, but by electrochemical process, electrochemical anodization. So these tubes are formed. This is very high surface area material, so it can detect parts per billion or a million level of the gases. So our intention was to detect the volatile organic compound coming out of the breath. So people have recently shown